A common enterprise pattern for search, recommendations, and insights is to store embeddings in a vector database and then use cosine similarity to find semantically similar results. I will demonstrate how you can convert hotel reviews into embeddings and then store them in PostgreSQL database using pgvector extension. I will then perform semantic search using natural language queries. I will also show you how pgvector enables hybrid search by combining the keyword search and vector similarity search. Before we begin, I want to share the steps that I have already taken in preparation of this lab. I have created a Postgres database using Amazon Relational Database Service. If you want to replicate this lab, you can create a database with default settings using Easy Create feature in RDS. Remember to note the master credentials that you create, as you will need them for connecting with the database. To make things easier networking-wise, you can consider setting up the database to allow public access and set up its security group to allow inbound and outbound traffic from all IP addresses. Remember, this is a highly insecure network setup and should only be used in a temporary lab environment. Also, remember to delete your database after the lab, as databases incur high charges compared with other services. Inside the database, under Connectivity and Security tab, you can find the RDS host that we will need for connecting with this database from our code. For storing the database credentials safely, I'm using AWS Secrets Manager. I have created a secret for the credentials that I will access from my code. Another thing I have done is to provide execution role of my notebook with permissions to access Secrets Manager. We need data for our lab, and for that I have created 100 dummy customer feedbacks for a dummy hotel called Luxe Lagoon. I have saved these feedbacks in this CSV file. Feedbacks have several fields including social media platform, date of review, reviewer name, hotel city, rating, date of stay, and the detailed feedback, which is a plain text field. I will store each of these fields in a database table that I will create, and for the plain text field, which is the detailed feedback, I will create a vector embedding and then store it in a vector data type in the database table. We need some libraries for our lab. We need pandas for data frames that we will use to prepare data for table insert. We need Boto3 to make API calls to AWS services. PsychoPG2 will help us make a connection with PostgreSQL database, and we will be able to run SQL commands. pgvector will enable our code to work with pgvector extension in Postgres database, and sentence transformers will allow us to create embeddings for feedback and query text. So let us install these libraries. We can import the classes that we need. In this cell, we are loading the feedbacks from the CSV file into the data frame. In the next cell, we are preparing the data for table insert. We are mapping the columns from the file into the column names that we will use in our data frame. And then we are converting review date and stay date to date time format and rating to numeric format. This will help us sort and filter our results during analysis. I'm also adding a new field called Review ID, where I will store the unique ID for each row. For simplicity, I'm using an incrementing integer value for the identity column. So this is the new column that we have added. As a next step, I'm generating the vector embeddings using a free-to-use and open-source embedding model called AllMini-LM-L6v2. This model generates embeddings with 384 dimensions, and this is a sentence embedding model which is trained for similarity comparisons between vectors of sentences or passages. So here I am embedding the review column, which is the plain text detailed review, and creating a new column called review underscore embedding to store the embeddings. So here this is the review and this is the embedding vector that has been created. As a next step, I am converting the vector embedding in a format that is required for table insert. So here I am converting each dimension of the vector into float 8 and then joining them using a comma and enclosing the entire vector string into square brackets. So this is how the vector string looks now. In this cell, we are creating two functions for interacting with AWS Secrets Manager. The first function, which is getSecret, extracts a secret from the Secrets Manager. We are creating a client for interacting with AWS Secrets Manager and then calling the API getSecretValue by passing the secret ID. Depending upon whether the secret is a string or base 64, we are extracting the secret and then returning it as a JSON. In the next method, we are extracting the password from the secret. In this next cell, we are using psychopg2 to make a connection with PostgreSQL. So here we are passing the host name that we saw in the database page, the default port for Postgres, which is 5432, and the database and user ID that I created when I created the database. We're extracting password from AWS Secrets Manager using the function that we just defined. And then we are passing an SSL mode of verify full. SSL mode controls encryption and identity verification of the server. Verify full is the most secure mode, which means that the connection is encrypted, the server's certificate is validated against a trusted root CA, and server's host name must match the certificate. To support this mode, we are also passing the certificate that I have downloaded from AWS site. After we create the database connection, we also need a cursor that is tied with the connection. Cursor is like an execution workspace for our connection, and it helps with running SQL commands. As a first step, we will install and enable pgvector extension in Postgres database if it is not already installed. Without this step, PostgreSQL will not understand the vector column. In this next step, we are creating a database table, Luxe Lagoon reviews, for holding our customer feedbacks. If you notice, we have a column called review underscore embedding, which is of the type vector and with 384 dimensions. This matches the dimensions of our vector. As a next step, we are inserting the rows from our data frame into this table. We need an index to do similarity search on the vector embedding column. The index that we are creating here is of the type IVF flat, and we are configuring it to use cosine similarity operator for similarity search. You have options of using dot product or Euclidean, but cosine similarity is typically used for similarity search. If you remember from previous sessions, IVF is an indexing technique for approximate nearest neighbor search. It sacrifices a small amount of accuracy for faster search over large volumes of vectors. IVF uses a clustering based approach by partitioning the vector space into clusters and limiting the search into a few clusters that are closest to the query. IVF has two parameters that we can set. Lists, which specifies the number of clusters vector space is divided into, and probes, which specifies the number of clusters that are searched for a query vector during similarity search. Lists is specified at the time of index creation, and the parameter probes is specified at the time of querying. Here, probes is applicable to our database connection only, whereas lists is applicable to the index that we are creating. After creating the index, we will also analyze the table to collect statistics about data distribution, such as number of rows, value distribution, data characteristics of columns, etc. These statistics will help the query planner to decide whether to use index scan or sequential scan. We are setting the probes to 5. Now that we have created our table, we have inserted the data, and we have created our index, the next step is to analyze the data. As a first step, we are creating a function that will embed the query using the same model that we used to embed the vectors that we inserted in the database. In this cell, we are doing a vector similarity search of the query text breakfast and food options against the vectors that are stored in review underscore embedding column. As a first step, we will embed the query into a query vector, and then we will define our select statement. Select statement is pretty standard except for this section where we are comparing the review embedding that is stored in our database with the query vector that we just created. And we are comparing them using cosine similarity operator. If you remember, we created our index to be optimized for cosine similarity. If you notice, we have 1 minus this expression, and that is because cosine operator returns cosine distance, which is 0 when vectors are similar and pointing in same direction, and 2 when they are opposite in meaning and point in opposite direction. 1 minus this expression gives us cosine similarity in the range of minus 1 and 1 being the most similar. So let's run this query. And we are limiting our results to 5 using this clause here. So here we have the results, no vegetarian option at the breakfast buffet, and here we have the cosine similarity. Breakfast hours are too limited. Ocean Terrace for breakfast is unbeatable. Breakfast was high quality. And breakfast buffet had incredible variety. So as you can see, all these search results are for breakfast and semantically similar to our query. In this next cell, we are doing another vector similarity search for a different query string, which is room quality and housing. And here we get 5 results. Let's see what we get. Housekeeping was inconsistent. Room was clean, but the walls were thin. Small but mighty, the rooms are a masterclass in space-saving luxury. Room had a musty smell, great views and friendly bellhops. The room service arrived in under 20 minutes. So as you can see, these are also semantically related to our query string. In this cell, we have the same query as above, except for this where clause where we are filtering the data based on our structured field stay date. We are filtering the feedbacks that have stay date over August 30th, 2025. So here you can see the filter has removed any review that was before the stay date of August 30th. If you see in our previous query, we had some, like we had these two. In this next section, we will learn about keyword search, which is supported by PostgreSQL, and how we can combine it with vector similarity search to do a hybrid search. In PostgreSQL, the keyword search involves two components, which are two built-in SQL functions. The first function is to underscore ts vector, which takes in the text that we have to search against, which is review in our case, and then creates a ts vector data type from this. Ts vector is an internal data type in PostgreSQL for keyword search. The function first splits the text into individual tokens, and then, depending upon the language, it applies language normalization. Language normalization can consist of various steps, such as lower casing of the words, removal of stop words, and stemming techniques, where the words are reduced to their root form. So here for this sentence, after removing these stop words, we are left with these three words, which are the root words for billing, issue, and room. You also see that we have the position of this word in the original word. And this is a TS vector data type. The next component is plain2 underscore TS query, which takes in the query text and the language parameter. And it does the same steps to the query string, which is tokenizing it and applying language normalization. In many cases, you may not want to do language normalization and you may want to search for the words exactly like they are. In that case, you can avoid sending the language parameter and send the word simple, which will skip the language normalization part. Another function that we will use is tsrank, which computes the relevance score for keyword search. It considers term frequency, how many times the query terms appear, and coverage, whether all query terms are present or not. So let us do one full text search or keyword search. Here the query text is parking garage, and we are going to search it in the review table, which is the plain text table where we have stored the customer feedback. Remember, we have two columns with customer feedback. One is review column that has plain text, and the other is review underscore embedding where we have stored the embeddings. Select statement is we will select some columns and we will also select the TS query and TS vector that are created by these functions, and then we will select the relevance score that is returned by the TS rank. And then we will filter the results based on a keyword search match. Here, this expression here means that there is a match between the query text and the review. So let's run this. And as you can see, for parking and garage, we have these two reviews. I see the parking garage here and I see parking garage here. Now, one thing to note here is that when we use this plain2 TS query, it adds both these words using an AND operator, meaning it looks for both words in the review. In the previous example, if you noticed, we did not pass the language parameter, and hence there was no stemming that was done to these words. What if we pass English as a language to the query text parking? So here English normalization has reduced parking to park, and all is good except that it is also retrieving feedbacks where we have the word park. So I just wanted to show this, that depending upon your use case, you may want this or you may not want this. In this cell, we want to search the three words using an OR clause. So what happens when we use these three using the plain to TS query? You will see nothing is returned because there is no feedback that has all these three words. It is because plain to TS query always adds an AND operator between the different words. If we want to do an OR search, we can use another function which is to underscore TS query. This function expects that you already put the operators between the words. So here I've already put OR operators between the words, and I'm using to underscore TS query instead of plain to underscore TS query. Rest of the syntax is the same. And you can see here I'm getting feedbacks where either of these words is a match. So here I can see there is beach word and hence this was selected. Here again there is this beach word and hence this was selected. Here we have the parking. Again parking. So you see the concept here. Now, as a last step, we will do the hybrid search. You can combine vector similarity search and keyword search into one query. Here I have the query embedding. Guests had issues with housekeeping, and I want to do a vector similarity search by comparing this query text with the vector embeddings and finding semantically similar matches. Whereas I have a query text towels where I want to do the keyword search and find all reviews where this exact word appears. So I've combined the syntax from queries above. I'm selecting some columns and then I'm selecting the TS query and TS vector that are created, and the relevance score for keyword search and the cosine similarity. I'm also returning a hybrid score which applies weightage to both of these. It applies 40% weightage to keyword search and 60% weightage to vector similarity search. And here in the where clause, I have two conditions. We want to return all reviews where there is a keyword search match or a cosine similarity match. So here you can see the three scores: text score, cosine similarity, and hybrid score. And this review has towels and therefore it was selected. Here I see towels. Similarly, I also see towels here, and hence we have a text score here. We have very low cosine similarity score because these do not align with our query text. Now here we have housekeeping was inconsistent. This is similar to our query text for vector similarity search. Again, awful, I had hair in the shower. Room had musty smell. So here you see that we get both keyword search and cosine similarity search in our results, which is called a hybrid search. So this winds up our lab where we used a relational database, PostgreSQL, as our vector store, and we learned how we can do semantic similarity search by storing our embeddings using pgvector extension. And we also saw how we can do hybrid search by combining keyword search and vector similarity search. We also saw that by keeping our vectors alongside other structured fields, we were able to apply filters using those fields.